Hello everyone, welcome to the course on data mining concepts. Myself, Dr. Sminu Isuddin, Associate Professor, Department of Computer Science and Engineering, Rajagiri School of Engineering and Technology. In this lecture, I'll give an overview on the topic data mining, motivation for doing data mining, and various data pre-processing techniques which need to be performed before doing data mining. This is the prescribed syllabus for the course. These are the textbooks and references, mainly concentrating on data mining concepts and techniques by Han and Camper. Why you need data mining, or what is the motivation for data mining? See, there has been always an explicit growth in the volume of data. Maybe because of the ease of storage, or maybe because of the ease of data collection, or maybe because of the computerization. Lots of data has been generated day by day. For example, maybe if you look at the business, maybe from e-commerce sites, or if you access Amazon or Flipkart, or when you browse it through the Google, or if you use some search engines to do your branch or a bank type of transactions, or if you go for any scientific area, like if you are trying to use some remote sensing images or biological data or scientific simulations, or maybe in even social media sites like something like Flipkart or digital photography or YouTube or any site if you use, and we can say that day by day a huge volume of data has been generated. But the issue is, even though data is generated, there is not enough knowledge being generated. We have lots of data, but we are starving for knowledge. So this give rise, or there is always a need for an automated tool to handle this massive data together, to generate some meaningful information or to generate some meaningful knowledge. So this gave birth to the subject data mining. Now let us formally define the term data mining. Data mining, it's a non-trivial process of extracting interesting, previously unknown and useful pattern or knowledge from a huge amount of data. So each and every of these terms are important. First of all, it is a non-trivial process, which means it's not obvious. The knowledge is not obvious. We need to be extracted. And next, it is implicit, in the sense the knowledge is inbuilt in the data itself. You just need to extract the knowledge from the data. And of course, there is a novelty part, which means that the knowledge has to be a new knowledge, and some unknown knowledge, previously unknown knowledge, it's a new knowledge we are generating. And finally, it is a potentially useful thing, that the knowledge we are generating is a useful thing. That again depends upon the application. So the knowledge often takes maybe in the form of some patterns in data, or maybe some regularities or some kind of structures in the data, or maybe from a huge amount of data that is also having some important aspect. Assume that for your application you are accessing some data. So the data which you are accessing may not be from a single database, may be extracted from multiple databases. So often we have to consider about the quality of the data. Okay, so there are mainly three questions which we need to answer. Now, what kind of quality problems can happen, or how do we know that there are some problems? And if I know that there exist some quality problems, how can you solve them? There can be several type of quality problems which may encounter. For example, you may have noise and outliers, which is the most important or the common problem which we find in data we access, or we may have missing values, or sometimes we can have duplicate values in the data. So all these quality issues you need to be addressed before you do the data or pre-processing step. Now we'll see this data quality issues a little more detail. The first one is noise and outlier. So outlier means any object which are having characteristics other than or outside the common property of that object. We'll call it as a outlier. For example, you can imagine like a salary value given as a negative number, so that can be an outlier. Similarly, another common issue is a missing value. So there may be many reasons for the entity to be missing, the data value to be missing. And the common missing value handling methods are you calculate or roughly estimate a value based on the other entries and replace it, or you ignore another method is you simply ignore the missing value entries when you do your analysis, or you replace with all possible values. You replace the missing value entry with all possible values. It may also happen that there may be multiple data items representing the same thing. This is common when we merge data from heterogeneous sources. Maybe, for example, the same person's record repeating multiple times. For example, the income tax data and the PAN card data of the same person, multiple entries, so it's getting repeated. So in the process of data cleaning, we should be very careful not to include such type of duplicates, because if you include, it will mislead the outcome, because the data mining algorithms will give result based on what it extracts from the data. So if the data itself is having these type of errors or duplicates, the outcome of the mining algorithm will be erroneous. So the pre-processing, it's indeed very important step, and it should be carefully dealt before you do data mining. As I already said, the data mining algorithms will give result only based on what it extracts from the data. So if the quality of the data itself is compromised, it will affect the knowledge generated. Data cleaning, data integration, data transformation, data reduction and data discretization are the major tasks in data preprocessing, which we'll be dealing in detail in the coming slides. The first step in data preprocessing is data cleaning. This includes filling the missing values, identifying and removing outliers and noise data, then correct the inconsistent data, and solve the redundancy problem which occurred due to data integration from different sources. Data may be missing due to multiple reasons. Some of the data may not be available. For example, maybe the income data fee attribute may be missing for some sales data. So all these missing data value need to be inferred. Missing data are dealt in multiple ways. In some cases, the tuple as such will be ignored, or in some cases we'll try to manually fill the data. Since it will be very tedious task, there are mechanisms by which we can automatically fill the data. Maybe we can divide into different classes, and you can replace the attribute value by the average value or the mean value of the class, or maybe you can take the mean value of the whole collection and replace it for the attribute, or you can have a probable value that you can infer using any mechanism, like maybe using a Bayesian formula or using a decision tree. You can infer the attribute value and you can replace it. Random error or variance in a measured variable is called a noisy data. So incorrect attribute value can be due to many reasons, like maybe because of the faulty data collection instruments, or maybe due to data entry problems, or data transmission problems, inconsistency in naming convention, anything. Binning, regression and clustering techniques are some of the common methods to deal with noisy data. Binning methods smooth a sorted data value by consulting its neighborhood, that is the values around it. The sorted values are distributed into a number of buckets or bins. And because the spinning method consults the neighborhood of the values, they perform local smoothing. And some of the methods by which you can do them are equi-width partitioning and equi-depth partitioning. This slide illustrates a binning technique. Here two methods are used: smoothing by bin means and smoothing by bin boundaries. So in smoothing by bin means, each value in the bin is replaced by the mean value of the bin. And in smoothing by bin boundaries, the minimum and maximum value of a given bin is identified as the bin boundary, and each bin value is replaced by the closest boundary value. So when you look at the example in the smoothing by bin means, the first bin actually we have value 4, 8, 9, 15. So if you are performing by smoothing by bin means, the mean value is 9, so all the bin value will be replaced by 9. But if you are smoothing by bin boundary, corresponding boundary, whichever boundary is closer, it will be replaced. So if I am performing smoothing by bin boundaries, 4 will be 4 itself, last value 15 will be 15 itself. The second entry 8 is more closer to 4, lower boundary, so it will be replaced by 4. Similarly 9 is also more closer to 4, so it will be replaced by 4. And when you look at the second bin for smoothing by bin means, the bin value are 21, 21, 24 and 25. The mean value is 23, so all the bin value will be replaced by 23. Now for bin 2, if you are using smoothing by bin boundary, when you take the second entry 21 is same as the lower boundary, so it will be 21 itself. But if you take the third entry 24 is more closer to the upper bin, so it will be replaced by 25. Now for the last bin 3, the values are 26, 28, 29 and 34. The mean value is 29. So smoothing by bin means all the bin will be replaced by 29. But for smoothing by bin boundary, second entry, it's more closer to the lower bin, boundary of the bin, so it will be replaced. 28 will be replaced by 26. Similarly 29 also will be replaced by 26. Next method is regression. So for regression, the data can be smoothened by fitting the data to a function, maybe a regression function. So we can have linear regression, which involve finding the best line to fit two attributes, so that one attribute can predict the other one. And if you are using multiple linear regression, it is actually an extension of a linear regression. So here more than two attributes are involved, and the data are fit to a multi-dimensional surface in a case of a multiple linear regression. So shown here is an example for a linear regression. And the last method is clustering analysis. So here outliers can be detected by clustering, where similar values are organized into groups or clusters, and value that falls outside the set of any of the cluster, they are considered to be outliers. Data cleaning also includes data discrepancy detection, data migration and integration. The next step in data pre-processing is data integration. It may often happen that your data you access, it comes from multiple sources. So we have to integrate data from multiple sources into a single data warehouse. So the sources can be from different areas, like it can be from multiple database, it can be from data cubes or flat files, anything. So there are a number of issues we need to consider when you integrate these data. For example, this schema integration, where or how or equivalent real world type of entities dealing with multiple data sources. how you match it, which is actually referred to as the entity identification problem. So all these problems we have to resolve. Redundancy is another important issue. Maybe an attribute, for example, maybe an annual income or something like that, which can be a derived attribute, something derived from a set of attributes. So inconsistencies in this attributes or the diamond or the naming convention, it can cause redundancies in the resultant data set. So often these redundancy problem we can solve it using, or we can detect it using, correlation analysis. So the redundancies can be detected by correlation analysis. Maybe given two attributes, such analysis it will be able to tell how strongly one attribute implies the other, or maybe based on the availability of the data how one attribute is related to other, that we can find out using correlation analysis. And for categorical type of data, we can use chi-square test, which is actually a correlation relationship between two attributes. Example for a chi-square calculation is given here. For numerical data also we can do correlation analysis. Given two attributes, such analysis will able to measure how strongly one attribute implies the other, maybe based on the availability of the data. For example, for numerical attributes we can evaluate maybe what is the correlation between two attributes A and B by computing the correlation coefficient, which is also known as the Pearson's product moment coefficient, as given in the equation. The third step in data pre-processing is data transformation. In data transformation, the data are transformed or consolidated into forms which are appropriate for data mining, and it involves different steps like smoothing, aggregation, generalization, normalization, and attribute or feature selection or feature construction. First step in data transformation is data smoothing, which involve removing noise from the data. So it involves techniques like binning, regression, and clustering, which we already discussed. So the next method is aggregation. So in aggregation, a summary or an aggregation operation is applied on the data. For example, maybe from the sales data you aggregate the sales data and you compute the monthly or annual information. So the steps here typically involve constructing a data cube for the analysis of the data. The most important step in data transformation is actually normalization. So here the attribute data are scaled so that they can fall within some specified range, maybe between -1 to +1 or between 0 to 1, etc. The different methods can be used: min-max normalization, z-score normalization, and normalization by decimal scaling. They are the popular methods. The fourth step in data pre-processing is data reduction. So these are the techniques which are applied to obtain a reduced representation of the data set, or the data set which is much smaller in volume, but still it maintains very close relation with the integrity of the original data. That is, we can mine on this reduced data set. It should be more effective, yet it produces the same analytical result. And some of the common strategies for doing data reduction include data cube aggregation, attribute subset selection, dimensionality reduction, numerosity reduction, and discretization and concept hierarchy generation. Now we'll see the first strategy, that is data cube aggregation. Now imagine that you'd collected data for your analysis, and this data consists of sales per quarter for past 2 years, that is from say 2018 to 2020 quarterly sales detail. But what you are interested only on an annual sale, that is total year sale or a total per year data rather than total per quarter data. So thus the data you have, that is the quarterly data, you can aggregate so that the resultant data summarizes the total sale generated per year instead of per quarter. Okay, so this type of aggregation we can visualize using data cube aggregation. So here in the case of data cube aggregation, the cube created at the lowest level of abstraction, that we'll refer to as the base cuboid, and this base cuboid should correspond to some individual entity of interest, maybe such as the sales details, or this lower level cube or the base cuboid generated, they should you should have the aggregated data for the individual entity. And from this base cuboid at the top level, what you have, you will call it as an apex cuboid. For example, for this sales type of data, the apex cuboid may be the total sale you want, maybe for a 3 years. So that can be visualized as the apex cuboid. It will be more clear once you see the figure given in the next slide. So here the base cuboid may be the quarter data, that is Q1, Q2, Q3, Q4 quarter data, that can be the base cuboid. And the apex cuboid, that the total data, the final product you want is statistics about 3 years, so that can be the apex cuboid. The next data reduction technique we are considering is dimensionality reduction. The problem with the higher dimension data is, the more the dimension is, the more number of attributes, which means it is more difficult to model the system in terms of both time and complexity. So you should be able to reduce the dimension as much low as possible. So to reduce the memory and the time requirement, and again for the easier visualization, we have to eliminate irrelevant attributes. So there are many methods to do that: principal component analysis, singular value decomposition. All these are methods which can be done to reduce the dimension of the data. One technique is principal component analysis, where you try to find out a projection that captures larger amount of variation in data. Suppose the data to be reduced consists of tuples or data vectors. Maybe if I can represent it by n attributes or dimension, then this principal component analysis or PCA, it will search for k n-dimensional orthogonal vectors that can be best used to represent the data, where the value of k is lesser than or equal to n. So the orthogonal data are thus projected into a much smaller space, and hence we can reduce the dimension of the data. So unlike other attribute subset selection methods, which reduces the attribute size by retaining a subset of the initial set of attribute, here PCA combines the essence of the attribute by creating an alternate smaller set of variables. That is, the initial data can then be projected onto this smaller subset, and this PCA often helps to find the relationship that are not previously found in the original result. Next method is wavelet transform or discrete wavelet transforms. This DWT or discrete wavelet transform, it's a linear signal processing technique that can be applied to a vector of data. So if we apply that to a vector of data, it will get transformed into another data vector x dash, and this will call it as the wavelet coefficients. Next is attribute subset selection. So attribute subset selection is actually a method which reduces the data set size by removing irrelevant or this redundant attributes. So the goal of this particular method, it is to find a minimum subset of attribute such that with this minimum subset, the resultant probability distribution of the class, it can be very much close to the original distribution. And various method for attribute subset selection are brute force method, where you do a trial and error method, then embedded approach, filter approach, and wrapper approach. The last method under data reduction is numerosity reduction. So this is a method to reduce the data volume by choosing alternate method or smaller forms of data representation. So there are two types of methods, parametric method and non-parametric method. In a parametric method, a model is used to estimate the data, so that typically only the data parameters need to be stored instead of the actual data. Log linear model is an example for parametric method. Example for non-parametric method include clustering, histograms, and sampling. Regression and log linear models are example for parametric method. Already we have considered this in the previous slides. Moving to the non-parametric method, the first one is a histogram. Histograms use binning to approximate data distribution, and it is one of the most popular data reduction method. A histogram of an attribute partitions the data distribution of that attribute into disjoint subsets or buckets. If each bucket represents only a single attribute value or a frequency pair, then these buckets are called singleton buckets. Or if they represent continuous value, they can represent continuous values also. In some cases, they will represent continuous values. There are different methods, or there are several partitioning rules: equal distance, equal frequency, maximum difference. All these are examples. Next method is clustering. Clustering techniques consider data as objects, and they partition these objects into groups or clusters so that objects within the cluster are similar to one another and dissimilar to objects in other cluster. We will see clustering in detail in module 4. The last one under non-parametric method is sampling. Sampling is used as a data reduction technique because it allows a larger data set to be represented by a much smaller random sample set or a subset. And the different methods which can be used, or the different types, are simple random sampling, sampling without replacement, sampling with replacement, and stratified sampling. Next pre-processing method is data discretization. So what do you mean by data discretization? It means that suppose we have a continuous data, we can represent them by some intervals or discrete bins. For example, if you have age of a person, we can give them in the range 10 to 20, 20 to 30, etc. There are different methods to do this data discretization. You can divide it in based on their frequency, equaling intervals, or you can use clustering methods. Discretization techniques can be categorized based on how the discretization is performed, such as whether it uses the class information or in which direction it proceeds. If the discretization process uses the class information, then we say it is supervised discretization. Otherwise, we'll call it as unsupervised. So if the process start by first splitting one or a few points to split the entire attribute and then repeat it recursively on the resultant interval, then we'll call it as top-down discretization or splitting. But instead of that, if you start by considering all of the continuous values as a potential split point, then remove some of the merging neighbor value to form intervals and then recursively apply this process to the resultant interval, then we'll call it as bottom-up discretization. Again, discretization can be performed recursively on an attribute to produce a hierarchy or something like a multi-resolution partition of the attribute values. And if you do that, then we'll call it as concept hierarchy. Or these concept hierarchies, generally they are useful for mining at multiple levels of abstractions. It is really difficult to manually specify the concept hierarchy for numerical attribute because of the wide variety or wide diversity of the possible data ranges. Hence, this concept hierarchy for numerical attributes, they can be constructed automatically based on data discretization. Now, some of the methods used for doing this are binning, histogram analysis, at entropy-based discretization, chi-square merging, cluster analysis, etc. Of which binning, histogram, clustering we already considered. Now we'll see what do you mean by this entropy-based discretization and chi-square analysis. Entropy is one of the most commonly used discretization method. Now in entropy-based discretization, it is a supervised top-down splitting technique. It uses the class distribution information to calculate and determine the split points. So to discretize a numerical attribute say A, the method select the value of A that has a minimum entropy as a split point and recursively partition the resulting intervals to get a hierarchy. Now let us assume that, see this with an example. Let us assume that set D consists of the tuples defined on a set of attributes with their class label. So this class label attribute will provide the class information for that particular attribute, that particular tuple. So the basic method for entropy-based discretization for an attribute A, it can be summarized as given in the slide. Each value of A, the attribute A, it can be considered as a potential interval boundary or a split point. That is, a split point for A can partition the tuple in D into two subsets satisfying the condition all the values with all the tuples with the attribute value of A lesser than or equal to the split point, it will fall in one set, and equal also, let us consider it fall in the one set, and the other set, that is other set will consist of tuples with the attribute value greater than the split point. So here we can get something like we want something like a binary discretization. Now in entropy based discretization, for example, if you consider two classes and we hope that all the tuples say the class C1 will fall into one partition, and all the tuples of class 2 that will fall in the other partition. But it's not always the case. Okay, so we have to consider, maybe we have to maybe in some cases it may happen that the first partition may contain some tuples of C1, but maybe for some partition it may contain many tuples in C1 and for some in C2. Or however, we may need some extra information to make a perfect partition like this. So this extra information, we'll call it as a expected information requirement to classify the tuples in A. And that is how we can calculate using the information value given in the slide, the equation, that is mod S1 by mod S into entropy of S1 plus mod S2 by mod S into entropy of S2, where here mod S1 and mod S2, they represent actually the total number of tuples in the set D1 and the first set and the second set respectively, and this mod S, that represent the number of tuples in set the actual set D. And now we can see here an entropy value. So the entropy, for example, we can assume that there are m classes. In our case we have only two classes. Generalizing, we can assume that there are m classes, m1, m2, m3, etc. m or c1, c2, c3, etc. cm. This entropy of your set S1, it can be calculated as entropy of S1 equal to minus of sigma I ranging from 1 to m pi into log pi, where this pi, it is the probability of class Ci in in S1, and like that we can calculate the entropy of S1 and S2. Now this process of determining a split point is recursively applied to each partition obtained until some stopping criteria is met. Stopping criteria we can set maybe something like the minimum information requirement to do a split point, which is lesser than some threshold value, where the threshold value we can fix. That is how you do entropy based discretization. Next one is chi-merge, which is actually a chi-square based discretization method. And this discretization, it uses bottom-up splitting up method. The previous one which we consider entropy based, it was a top-down approach. Now here it uses a bottom-up approach to find the neighboring intervals, and then here it uses the bottom-up approach to find the neighboring intervals and then merge it recursively to get the larger intervals. So this is also a supervised method, which means here also we need class information. So the basic information is that for accurate discretization, the relative class frequency should be fairly consistent within the interval. Therefore, if two adjacent intervals have a very similar distribution of classes, then intervals are merged. Otherwise, they will remain as separate. So, the chi-merge follows like what shown in the slide. The steps are shown in the slide. Initially, each distinct value of a numerical attribute, say A, it is considered in a one interval class set. Now, chi-square tests are performed for every pair of adjacent intervals, and these adjacent intervals with the least chi-square value are merged together, because a lower chi-square value for a pair, it indicates that the similarity exists between the classes, and this process repeats recursively until some predefined stopping condition is met. Next one is segmentation by natural partitioning, also called discretization by intuitive partitioning. So here we use a 3-4-5 rule to segment numerical data into relatively uniform intervals, and here the rule it partition a given range of data into 3, 4 or 5 relatively equal width interval, and the methods or steps to do that is given in the slide. All the previous explained method try to generate a concept level hierarchy for numerical data. Now we have to do this for some cases for categorical data also. So categorical data means they are the discrete data, or the categorical attribute they have a fine number of discrete values. They may not be having ordering among the values. Now there are several methods to generate concept level hierarchy for categorical data. It is given in the slides. You can use specification of a partition or a total ordering of attributes. We can use specification of attributes for a set of values by explicit data grouping. You can use a partial set of attribute, or there are automatic generation of hierarchies by the analysis of the number of distinct values. Example for a automatic concept hierarchy generation is given in the slide. And now suppose we want to generate a concept hierarchy based on the number of distinct value for some attribute. Suppose if you want to select the location oriented attributes, say the street, city, state, country, etc. Based on that you want to generate a hierarchy. Now this can be done like, first you sort the attribute, these individual attributes you can sort them in the ascending order, and you identify the number of distinct values in each attribute. Now this will result like, for example, in for country you have 15 distinct entries, then for state you have 365, like that. For 60 you have 3567, and again for street you have again a larger value, distinct entries. Now in the second level you generate the hierarchy from the top down according to the sorted order, with the first attribute at the top level and the last attribute at the bottom level. And finally you can generate the hierarchy. So that is how you can this is an example to generate a automatic hierarchy. As we conclude, we found that data preprocessing is a very important issue in data mining, and you need some descriptive data summarization methods to improve the quality of data. And we also saw some data pre-processing methods, including data cleaning, which help to fill this missing value or to remove the noise or outliers from the data. Then we saw data integration method, which can combine data from multiple sources, and later you can transform the data using some data transformation methods to convert to some approximate or appropriate method for mining. And we also considered data reduction techniques, which will help to reduce the size of the data, and we also considered the data discretization method to generate a hierarchy or to generate a form hierarchy from this data. These are my references. Thank you.